Hi, I'm Jot. I'm building houses that produce more energy than they consume. Within this video you will find out, basically it's a new way to heat up your house or your greenhouse, and I want to show you. So basically look, from 120 pounds of organic matter or like 54 kilograms of, let's say, junk like straw bale, hay bale, wood chips, sawdust, leaves, grass. Basically, you can gain 360 kilowatts of energy, like heat basically, and 79 kilograms of CO2 in case if you have a greenhouse. So is it a video about how to heat up your greenhouse or house with the compost? No, basically it's not, because that's not compost. Composting, it's like totally different. So let me show you the logic. 50 pounds of organic matter, or like 23 kilograms, let's say, it has 131 kilowatts. That's like insane. So imagine all that it's stored in chemical energy, and the only thing that we have to do is like backward engineer photosynthesis to, and again, that's not composting in a greenhouse. It's way more efficient. So probably the closest thing that you heard about, it's like the hot composting. I will give you the math and the recipe in a second. So the best example is, I read about it, it was a pot and they planted a little tree in the pot. And they measured the pot, they measured the earth in the pot, and they measured basically everything, the water, everything. And after a while, when the tree started to grow and it was like huge, then they took it out from the pot and they measured everything again. They measured the pot, they measured the earth, and they measured the tree. And the question is like, if the earth, it was the same in weight, because it remained the same, it was like basically irrelevant difference, so it was like almost identical. And the question was, okay, but how the tree appeared, because the pot is the same and everything remained the same. And the answer is the carbon. And what is photosynthesis? Photosynthesis basically from energy and from carbon makes organic matter. And now we want the cleanest way. Again, it's not composting, it's similar to composting, but it's totally different. So we want from organic matter to make clean energy and CO2, nothing else. So basically that would be the idea, to reverse engineer like the photosynthesis. And the trick is, probably all of us know about it and we use it, but the problem is we need to take it to the Formula 1 level. And I've seen many, like if not hundreds of videos that everybody's almost nailing it, but it's like a little difference. So there's hot composting and cold composting, and the whole issue, it's about the bacteria that we use. We are using the wrong bacteria in the wrong environment with the composting. So the key is the hot composting. However, the issue is that hot composting in 99% of the cases it's not efficient for others, because there's another type of bacteria, they're like the thermobacteria, and they die. So basically your compost starts to heat up, you have like one type of bacteria, afterwards they start to heat up even more, you have like another type of bacteria, they die, afterwards it comes like a third type of bacteria, like the thermobacteria, that's like the hot composting, and afterwards it starts to heat up way more than it should, and they're like not just one, but like 5, 6, 7, several problems, and those bacteria die. So your hot composting will start to go back, and it will go back to like the 30-40 Celsius, and we don't want that. Our own thing that we have to be like really like hyper focused to keep the thermobacteria alive, and I will show you how to do it. So if we can manage that, we'll have like almost limitless free energy. Let's say, okay, it's not like the perpetuum mobile, but just look at the numbers, you know. And again, I finished architecture, so I'm not a chemist, I'm an engineer, that's my calculation, and for me it kind of works. So it's not like that's a rule that I say, oh, those are the numbers. I'm just saying, hey, let's talk about that are my calculations, and I made it and it works for me, you know. And if you want to collaborate, I can show you everything, like just write me an email or something and I'll show everything that I got, that it's not in the video. So yeah. And where we messed up, so think about it again. So when you have the cold compost and you want to go to the hot composting, it warms up, it's great, and after 2 days it will die down. And we to continue, we start to move the compost and we say, oh, it needs air. Yeah, but why it needs air? It needs air because it needs oxygen. And it's not about the oxygen. The biggest problem is, like when you give the oxygen to the thermobacteria, it's happy about it, it's cool, it's perfect. However, meanwhile we cool down the pile, so it's going down. And it will dry out. So we need to water it again, and how we water it? With cold water. So what happens? It will it will die again. So we can't do that. We have to insulate the whole thing, and it has to be inside in an insulated chamber, you know, be it a static version that I'm showing to you, or be it like a moving, like a rotating one, because I built 3 versions, and the first 2 versions were like that. That's the third version that it's like the interior is moving, not the whole material, it's not rotating. And for me, the funny part was it's not that the bacteria, the anaerobe thermobacteria needs the oxygen. Not the oxygen is the problem. The problem is the CO2 is killing them. Like imagine yourself, if unfortunately we are like in a chamber, we are like locked up, we won't run out of oxygen. We won't die off because we don't have the oxygen in the air. We will die suffocating by the CO2. So the bacteria has the same problem. Wait a bit, I'm showing you. And again, I'm not a chemist, I finished architecture, so you can ask me about like engineering, architecture, I can respond and it will be like on the spot, it will be like perfect. But here, let's say I made my homework, I worked months on the issue, and that are my calculations, and they are not correct, please correct me or like hit me up and we'll talk about it. But look, after my calculations, like 120 pounds of organic matter to be decomposed, or like 54 kilograms of organic matter, we need to give the bacteria 237 square cubes of air for the oxygen. Can you imagine? That's like insane, like that's a lot. And when we say like, oh, we have to turn the pile and it will work. No, dude, like look, it's like 237 square cubes of air movement just to provide the oxygen needed for the bacteria. Can you see the difference? Like it's like a Formula 1 of a Formula 1 of a Formula 1 efficiency. So they're like working like crazy, you know? And the other thing, it's not the oxygen. So that was the oxygen, but we need to eliminate, and there's the key, 466 square cubes of air to eliminate the CO2. So the CO2 is not suffocating or killing the aerobe thermal bacteria. Can you imagine? Like, that's insane. And that will produce 360 kilowatts of heat after my calculation. So again, I'm not a chemist, I'm not an engineer, please make your I'm not like a chemist engineer or something, please make your calculations, those are mine. And actually what happens here, so the thermal bacteria, it's so efficient to decompose everything that it will kill the harmful bacteria, because most of the bacteria that are harmful for us live in the temperature that we live at, isn't it? It makes sense. So everything that's above, let's say 60 degrees Celsius, I have no idea what it's like in Fahrenheit, but most bacteria die there, you know. Like if you keep the bacteria, the thermobacteria at like a 60-70 degrees, then the odds are most of the harmful bacteria to humans and for the plants, it will die. Basically they will eat the bacteria or like the viruses, everything. Sorry, they won't kill the viruses because the viruses are not living, but they will decompose the viruses and they will kill the bacteria, they will eat them alive, something like that. So it's like really efficient. It's like really unharmful for humans. And what I read about, so again, I'm not an expert, I'm more about architecture and engineering, not about chemistry. That was, yeah. And they say, but the huge difference here, nothing is rotting. So basically, absolutely nothing is rotting in the inside. So you don't have the rotting smell. Why should it smell like rotting? The only smell that you like is definitely a smell. It's not like a thing that you want to live in that, but it won't bother. It's not bothering you. So if you have it in a greenhouse, or like if you do it like in a really clean way, so you have like the thermal bacteria and you don't have like the mesobacteria that's like working at like 30-40 degrees, that means you almost won't even feel the smell of it. Because So it will be an odor, it will be, but it won't be rotting. So it will be like an extreme difference between the two. So it's like another level. And the main idea is you have the machine and you start to put things in it. You put it in it, in like 2 days you put it again, in a day again and again and again, and basically it disappears because most of the things, it won't be like, it won't transform itself in like humus, or it won't be like earth. It will be, as mentioned, energy and CO2. Quite simple, we have to just measure like 6-7 things, like the water, the air, the CO2, and we have to adjust it, because if it's too hot, then we can adjust it, like saying like, oh, it's too hot, then we are not giving it water, you know. Or if it's like it gets too much air, that means the bacteria starts to work even better, so we say, oh, don't give them that much air, you know. So basically there's like 6-7 things that we have to measure constantly, like, and giving a feedback, you know. And the main idea is not to kill and to keep the thermobacteria alive. We have to give them the oxygen, we need to give them like, we need to eliminate the CO2, and basically that's it. So it's a little bit complex, probably I will write it down because it will be easier for me than explaining, but you need to measure a few things. But afterwards you will decompose things, and again, it's not composting for greenhouses, it's not like a normal composting, because it's not, I'm not sure, like I'm not a chemist here, but I think it's not composting, it's something else. But it works like extraordinarily well. And you can warm up like hot water in it. If you put something in the machine, you know, like the tubing, that you can warm it up, like the hot water, and you can have like almost limitless amounts of hot water, and it's way more efficient like the normal composting again. And you can use the air as well, because you can put the whole thing in the greenhouse, and it will keep the greenhouse alive, and it will. So it has several advantages compared to normal composting in a greenhouse, because if you think about it in this way, if you have in every greenhouse of yours a machine like that, or like one in like several, and they're like combined with some tubing, you name it. But the main idea is then you can like close the greenhouse. You can put like a nylon house, like a polytunnel, and you can close it, because if it's closed, then the cold air, it's not going in the inside. And again, you don't have to take the cold air from the outside to take the CO2 for the plants, because you already have it there. So this way you will be maybe a few weeks earlier in the season with your plants, because you start earlier. It's way warmer in your greenhouse, so the plants will grow better. So that's one thing. The second one, because you have the CO2 in the greenhouse, you have the greenhouse effect, just because, let alone of the of the CO2. So that means the greenhouse effect itself in the greenhouse from the CO2 will heat up your greenhouse even better. The third version, it's basically because you have like the humidity in it that can keep it like warmer even better. So basically it's like a layer, and a layer, and a layer, and it doesn't cost you almost everything. So for me to run this machinery, it cost me like a 30-40 watts, maybe 50 watts per hour or something like that. So I'm telling you where most of us would mess it up. So first we have to insulate it. So think about the logic. When you put the material in it, you put the proper ratio, like the carbon, nitrogen 1 to 30, 1 to 35, something like that. And afterwards you're ready, you close it. Like it's closed, everything is closed, and you put like 10 or 20 centimeters of insulation in it. I'm not joking. You have to insulate it, like at least that, like 15 centimeters, wait a bit, 6-8 inches of like R30, like that insulation. You insulate it and you leave it like that, like a day and a half, like 2 days depending, till it reaches like a 44-45 degrees. Because here catch so the logic is, first the anaerobic mesobacteria starts to warm, like slowly. It will be like a really slow process, you know. It will take, even if it's frozen in the inside, it will take even more. Maybe it will take like from 1 day to like 3 days, depending on the material what you put in it, you know. So it depends from many things. But it will warm up, and when it reaches like the 45 degrees, then after then it will start to work for your advantage. And just after then you open it slightly, because if you don't have the thermobacteria, you don't need the oxygen, and you don't need to eliminate the CO2. You don't care, you ignore it, you close it, because 90% of your focus will go preserve the heat in the inside. You know, you don't want to open, you don't want to, oh, let's see what's in the inside. No, you don't open, you leave it, you know. You're not even going in the proximity of the thing. And afterwards, it starts to heat up like, let's say, a 40 degrees Celsius. And then, like a 45 degrees, then you start to give them like a small little, like, just show them air, you know. Imagine like a little ventilation. For that monster that we have here, you need the ventilation like, imagine like a fan like that big, you know, like basically nothing, you know. You put that and you leave it for a few hours. And afterwards, you start to ventilate it with like computer ventilation, you know, that you have for the computers, like those ones. And with that version, I don't want to tell you like, oh, you need to, because it has like a calculation and made the calculations with Excel. So if you want to build it, just drop me a line and I will help you to do it, you know. I help you for free, so it's not about that, but I don't want to like give like some advice that I didn't double check. So yeah, I'm telling you, in my version, I used like two vents. One was like 300 square cubes of air in an hour. That was like the inside that pushed the air in the inside. And I had, I think, one that was like grabbing the air out from the machinery. That was like a 250 square cubes of air every hour, something like that. And there's a catch. Even so, when the whole thing starts to warm up, you have like when you have like 200, 300, 400 kilograms of material in it, like a lot, let's say for a huge greenhouse. Even so, you don't push the cold air in the inside and you say, oh, it's not cold. No, if it's below 45 degrees Celsius, trust me, it's cold. So basically you do it the following way. I put the pipe on the ceiling. Like imagine like the really thin pipe, like I think it looks like aluminium. I'm not sure about the material. I didn't make a picture of it, but imagine something. It's like paper, you know, but it's like aluminium foil, something like that. And I put like 5 or 6 meters on the ceiling, you know. It started to move like that. And why? Because I push the cold air, let's say at 25-30 degrees air. Even in the summer, the 30 degree air or like a 40 degree air is too cold, you know. And you have those things on the ceiling, and because the hot air goes to the ceiling, it will heat it up. So the air has time to warm up to like a 50-60 degrees Celsius till it gets up. And afterwards, the fresh air with the oxygen and without the CO2 will go into the machinery. And from another part, from the lower part, you just take out the CO2 and you push it in the basement. At least I did so. I thought to my uncle, hey, don't stay in the basement. I didn't really taught him exactly what's happening here, but you can we had like 2000 ppm parts per million CO2 in the basement, so it wasn't like that dangerous. But I feared a huge basement. We have like a really big house, let's say, and the basement was like full of CO2 like really quickly. And afterwards I started to open the windows and everything, because I said, oh, that's way more that we need there for the... We didn't even have flowers. I just wanted to make like demonstrations for myself that it's working. And in the outside, I think it was like a minus... It was freezing, so I think it was like a -7 or 8, because I know I put the whole thing under a nylon sheet, and it was like the insulation, and I have to stretch myself under the ice to go to the machine. So it was like made in a Balkan way, let's say. It wasn't like packaged like the new iPad, we can say that. Even so, I had like 6 or 7 meters from the machinery to the house, to the basement, and I had a pipe without insulation, without everything, and even so, it pushed hot air in the basement, you know. So I think the thing was a success, and I will recommend you to try so. The fan that I have there, it was like, I think like a 6, 7, 8 meters away from the machinery, because the machinery wasn't in the basement, it was in the outside in the cold air, and I had the tubing and that wasn't insulated. But even so, I have like a 27 degrees that is pushed in the basement, you know. And it was like, we can say it was like for free because I got the materials for free, you know. It was grass. And look, 1816 ppm of CO2 for free, you know. And when I read about how much it costs, I don't want to get into it because probably you guys are like knowing like 1,000 times better than me that CO2 is not cheap to put it in the greenhouse, you know. So it's not a cheap thing to do so, but look, for me it was like for free, you know. And even so, it's 27 degrees, and if you want to do it with your house or like your jacuzzi or something, you don't have to push the air in your house, you don't have to push it directly, you just put some tubing in the machinery, you know, and you push the cold water in the machine and it will warm it up, you know, and you will have like extraordinary like a lot of hot water, basically limitless, not limitless, but we can say it will be more that you will use. And again, it's way more efficient than composting in a greenhouse, or like way more efficient than using composting for heating in a greenhouse, because it's working in a different way. It's superior, you know. It's like comparing a little donkey with a Formula 1 car. It's not the same. So I want to show you this one. It's like a really good one. It took me forever to like really believe it, and I have to recalculate it. And oh no! I'm showing you something different first. Look. So I had to recalculate this like 3 times because I didn't believe it, and I said like, okay, I'm not a chemist, but I couldn't like mess it up so wrong. So look, and probably I have errors in it, and again, I'm with the architecture part, engineering, like just don't pick on me. But look, the logic. So first, when I said, look, I have 54 kilograms of organic matter, and how on earth from 54 kilograms of organic matter I will get 79 or like 80 kilograms of CO2? Like, what's happening here? Like, you know, like it doesn't make sense. And I didn't understand like how on earth can that happen. And basically it's like really simple, because you put the 54 kilograms in the machine, but you're pushing the air in the machine, and the air has like the CO2 in it, you know. Sorry, not the CO2, but it has the oxygen in it and all of it, you know. So basically the whole balance will change. So that was it. I was like I have 54 kilograms, and probably I will have something like 2 kilograms of CO2 or 3 kilograms. And no, actually you will have way more, because the bacteria will start to eat up the oxygen, and you will start to eat up the organic matter, and it will produce way more CO2 that the initial organic material itself that we put. And it doesn't make sense, you know. It's like not an intuitive thing, like how on earth we give something like 50 kilograms and we have here like 80-90 kilograms for free, just for us. Especially we didn't pay nothing for the organic matter, because it's not like you have to buy the best, or like straw bale, or like you have to buy like the best material for it. No, it's like something that even like the horses won't eat it, you know. It started to rot, and like, let's say a little bit, or it's like the grass from the outside that nobody wants, you know, or like the leaves in the autumn. You just collect them and you start to use it. It's like junk, basically. Nobody wants it. And look, that's one of my favorite parts here, because it's like stealing. It's like stealing candy from little kids. Not that I should do that, or like you should do that, but look. So 100 kilograms of CO2, it's 27 kilograms of carbon and 72 kilograms of oxygen. That means like a 27-72. So basically, that's like, just imagine like you're pushing the oxygen in the inside on the spot. So let's say in the classical way, if you're like a greenhouse owner and you're like really rich, you buy the CO2, you know, and you start to use the gas, but you have to pay the shipment. Like say if you buy like 100 kilograms of CO2, you have to ship it there, you know, like the whole 100 kilograms of CO2, and you have like the really expensive equipment, and it would cost a fortune. I'm not going into that, but basically you have to ship the equipment there. And here you don't have to ship 70% of the equipment, because you provide the oxygen on the spot. You just like do like that with the ventilation system, and it will be in the inside. So it's not that the initial material is for free. Okay, you have to collect it, like somebody has to like cut the grass, or like take the hay that nobody wants, because there are hay bales that nobody wants, because if the, let's say, the horses, maybe the horses are not eating it, if some animal is not eating it because it has some problem with it, for you it will be like really good, I'm telling that. So let's say if you're like wise, you can manage the organic matter for free, like the leaves. Who wants leaves? Nobody wants them, so you collect them and you have the 27% for free, and afterwards you have the 70% for free again, you know. So it's like compounding, like a wave and a wave and a wave. Sure, my calculations maybe are not the most exact, and I'm not telling I'm the ultimate truth here. I just want to open a conversation here, you know, because we should use this, because it's like really smart and it's not harming the nature. It can heat up your house, you know, it can heat up your greenhouse, it can do like a lot of things. And there's like a crazy thing that you're not thinking about it, or at least I didn't. So imagine like the carbon, or like the materials that we use there. Like say like hay bale, straw bale, wood chips, sawdust. They're like different, and not in the same way. So basically the energy in them, you know, like the different materials, like say wood or like grass, are almost the same. So it's not like a huge difference. It's not like, oh, 3 times more energy in the, it's not like that. The only difference is like, that's like makes the difference, it's like the size of the wood chips. Imagine like let's say you have like 100 chicken and you start to feed the chicken, and if you put the food for the 100 chicken at once, they can't eat, because it's like the surface area, they want to eat, like the bacteria are like the chicken here, you know, they can't get to the material. So the smaller the material is, the easier it's to decompose it, you know, because it's more surface material to bacteria. So basically more bacteria can go in the same place to work. More bacteria makes more energy, makes more heat. The heat starts to make more thermobacteria, or it will make the environment for more thermobacteria. So it's like an avalanche, you know. So basically, if you want to like really max it out, then you use material that is small. Let's say sawdust is really good, but just be aware that it's like full of carbon, so, carbon, so you need a lot of nitrogen with it to have like the 1:30 or like 1:35 ratio. I'm not sure it's something like that. So again, I'm not the best gardener here, but you have to keep in mind that as well. And the best thing is like the best of the best, it's like the grass, you know, like if you have like the lawn, you know, because that's the smallest, and the machinery it's like cutting it for you like in the smallest pieces. So better than the grass, you don't have anything. And probably if you're like gardening, you know that, because it's the grass in 24 hours, even in the coldest winter, it will go up like in a hot compost. In like 36 hours it will be there. And I use that because I had the problem with the machinery with that version. So the problem here is the following. Actually, I wanted to put like 500 kilograms. Yeah, I have a grand amount, I have to admit, you know, like I wanted to build my first versions, you know, like big. I wanted to impress anybody, and I had an error here, a mistake. I didn't think about it, that even if I put like grass, because you can tell it's grass in the inside, and it was from the BMW's showroom in front of it, you know. I made friends with the gardener and he gave it to me. And I actually have them, so I worked for that grass. But the main idea is, it works super, it's perfect for like 12 hours, you know, like 14 hours. But afterwards, the whole thing starts to be like sticking and stitching, and it will be like, it will break everything, you know. You can't put a strong enough metal in it that it won't break, you know. So it was a problem, and probably you can solve it in a way. So let's say when the things are rotating, you know, sometimes they get stuck, and usually they will get stuck and it will break everything, you know, the chains, the machinery, it will like just bend the metal like nothing. So that composting the inside, if you leave it like there in like for a day or like 2 days, it would break everything, you know. That's why I didn't put more, and I was like praying not to break, you know, like, oh, I was in stress, you know. But you can solve it like really easily. I didn't continue with that because I started to do other things. But when you have this and it's moving, you put like something that it will let to sleep. Let's say you calculate it like you want to have like 100 kilograms of force in it, and afterwards it will start to bend, or you put something on it that will let it bend, you know, after like I didn't think about it, but if you do that, it will work just like fine, you know. Or I think if you want to, and what I like here again, that you won't get dirty. If you think about it, with the composting, like the normal greenhouse composting or composting to heat up your house, you get dirty because you will have the laughter gas that's harmful to humans, and that's harmful for, like, I think for plants as well. I'm not sure here, but I'm sure you don't want that. And you have like a lot of things like byproducts that you don't want, you know, like you have the methane and everything. I'm not an expert here again, but I know that with this clean type of composting, you don't have that amount of harmful material for humans or for like plants as well. So sure, the CO2 will kill you. It's not even a question. I'm just telling you, don't have the other byproducts that are like way more dangerous, because CO2, I wouldn't want to say like it's not dangerous because you can't feel it, but at least here you will smell it, you know. It's not like CO2 and you don't feel it, because when you go there, you feel it is there, and the question will be, okay, how much is in it? But everybody will ask like, what's happening there, you know? It's not like you're dying. And the other thing, like, you won't let it accumulate more than like 200 ppms, 2000 ppms, because you have to be careful. So yeah, I don't found it dangerous. I think it's like a really good solution. And look, if you check the videos at the left, you can tell it's not like dirty. It's not like, oh, you look in the inside and you will faint, you know. It's like, sure, it's like an organic material, it's working, things happen, you know, it's like bacteria working, but it's not like something that's like rotting. It's nothing is rotting here, and you can put your hands in it, and sure, it will be like hot, but afterwards nothing bad will happen to you, you know. Like, it's compared, you know, because everything is harmful at one point. But I'm telling you, it's not like, oh, you have to go in a place that you can't even like resist the odor, you know. It's not like that. The more that once I tried, because one of my friends is like in a franchise with Dalmayer, like the coffee company. They are having like coffee machines, and I had like maybe a few hundred kilograms of coffee grains from him, and I put that with hay bale, you know. I made a composition with like 1 to 30 or 1 to 35, I'm not sure here, probably you guys correct me because you know it better than me. And it smelled like really good, like for a whole day. It smelled like coffee in the base. So check it out, in the basement, 1600, 1700 or 800 ppm, and it's not on the ventilation, it's in the whole basement. Basically I could go ever in the, and we have like a huge basement, and I'm not sure here because I'm telling you again, I'm not like the best with the plants here, but I think if I remember, the gardener said that usually for the most plants that's the level you want. So I tried to achieve that, you know, and again, our basement is huge, and it was like that. Yep, so that's what I want to tell you in this video, and if you want help, just drop me a line and I will try to help, you know. It's environmental friendly, it's cheap, you don't need like a lot of resources, because I know it was like that guy, probably I'm not pronouncing his name right and I'm not even remembering it. It was Shaolin Koshla, something like that. It was an employee of the Canadian government, and he made a study about, again, I'm not in the topic that much, but he made a study that to use like proper CO2, it would cost you like 100 grand per year, something like that. Like the initial investment in like CO2, not the CO2, like the CO2 equipment, you know, and all of it, and afterwards you have to have like another investment with the, not just the machinery, but the CO2 itself. So basically it will cost you easily like 100 grand per year, even more, you know. And that thing, it cost me, that machinery, it cost me like maybe okay, I didn't use like metal, I didn't use like plywood, I made it from ferrocrete, that was the cheapest, and like the HDP, I think that, so basically it's like a plastic, one of the strongest plastic that you can find, you know. And I put the insulation in it, so I think the whole thing, it cost me like 300, maximum $400, you know. And it's like a big difference between like $400 or like $60,000, you know. And afterwards, like the things that you have to pay like monthly, it's like 100, 200 watts. So basically it's like ventilation in, ventilation out, like 300. I'm not sure, I think it uses like 40 watts per hour, I'm not sure, but I know it moved like 300 square cubes of air, the first one, and the second one it moved like 100, no, 250, something like that. So I think the overall usage, like the not the usage but the price, it's like maybe 100 watts per hour at maximum, but not even that, something like that, even less. And it's like for a huge greenhouse, even more like for an industrial greenhouse, you know. And most of the persons don't do that. I was just like really scared because of the cooling down the bacteria, and I said, oh no, I'm making it big, because if it's big, then the bacteria will work, it will start to eat, and it won't cool down. But as I told you where I have the mistakes, but yeah. So that's the video. I think it was like longer than I wanted, because I'm not that good with the speaking, but that's today's video. And if you have questions, like drop me a line, or like write a comment below the video, and I will try to respond to everybody, because I'm not Mr. Beast yet, so probably I will have the time to to respond. Okay, see you in the next video, and subscribe. Bye bye.